Robots are mechanical systems, so they will wear and change over time. This can lead to unnecessary maintenance or unplanned downtime if not caught in advance. If these changes are not understood, the tool center position, TCP, is likely to shift and require the robot to be reprogrammed. However, this can mask underlying issues and before long a critical failure will occur. By periodically monitoring key metrics such as path performance, repeatability and backlash, a better understanding of the robot's state can be gained and repairs or fixes planned. Equally, short-term changes caused by temperature and variable payloads could impact the TCP location and can change over the course of a day if not tracked. If you aren't monitoring something, you don't know how it is changing over time, and this can hide issues until they become unavoidable. Before discussing some of those performance metrics in more detail, a quick note on accuracy and repeatability, which are separate concepts. Accuracy describes how close to a target you are, whilst repeatability describes how close all your points are to each other. If a robot is repeatable, it will keep going to the same position, which is important to run applications. Joints will wear and degrade over time, and backlash caused by give in the gear trains, where approaching a position from different directions yields a different result, will have an impact on process repeatability. This can be monitored using an RCS L90 ball bar and highlight when a repair is required. The RCS repeatability tests are bidirectional and can be configured to exercise individual or all axes. By measuring the repeatability from two directions, the difference between the two repeatability results will show the backlash. This can be set as a baseline and monitored for degradation over time. Additionally, repeatability isn't uniform across the working volume, as different axes will affect different areas. Finding a local repeatability can be a useful tool to determine the most suitable location of the working volume to situate a process requiring a higher degree of repeatability. Another metric to track is the path performance of a robot in a given volume of the working area. This is easily performed with an RCS L90 ball bar, which describes a series of arcs and circles in different planes and indicates how close to the nominal a robot can perform. This test is called a volumetric test. This is a useful test to carry out as it indicates the baseline performance of the robot. If it is then repeated after an intervention, such as updating joint offsets, or a physical repair, a view of how the robot has improved can be seen. Using the RCS L90 to track path performance against individual axis moves provides data to show the effects of bending, gravity, and reversal spikes, so they can be isolated and corrective actions taken. In addition to path performance in a single plane, using the RCS T90 tripod configuration of ball bars, full 3D path performance of a loaded robot can be understood. This is important as a robot's physical setup can be quite different to its digital representation, with cable packs, end effectors, and other materials affecting its actual performance. By being able to track the 3D TCP path when under normal operating conditions, a better understanding of the application performance can be gained. This feedback can then be used to update and adapt the program being run, so real-world factors can be compensated for and the operation carried out in a closer way to that intended. In short, the RCS L and T90 kits provide a standard approach to running diagnostics and performance tests. They can provide a historical view of a range of metrics which will indicate the current expected performance of the automation cell and flag the need for maintenance well in advance of issues occurring. They also can help the setup of new processes by indicating regions where higher repeatability and path performance can be achieved.